Namaste student, namaste everyone. And here are some MCQ multiple choice questions which are not in the order as per the board exam model question paper. So they are very different questions. That's why I have selected it. Let us have a look into all the questions. The quantization of charge was first suggested by the charges are always quantized. The charge on a body is an integral multiple of charge of electron. So these are some of the examples where we have some questions from the corners of the book. It was first suggested by Michael Faraday. The quantization of charge was suggested by Michael Faraday, and then it was experimentally proved by Millikan. So the next question. Quantization of charge was experimentally demonstrated by Millikan, and his famous experiment, Millikan's oil drop experiment, that proved that charges are quantized. The charge on a body is an integral multiple of charge of electron. So n can be plus or minus 1, plus or minus 2, and so on. So it was proposed, or it was suggested by Faraday, and that principle was given by Faraday, whereas it was proved by Millikan. Okay, third one. A cylindrical Gaussian surface is placed in a uniform electric field as shown. Electric flux to the cylinder is. So the charge is not inside the cylinder. Remember, the electric field is here and the electric field is here. Electric field lines are crossing like this. That means the charge should be outside. And flux through a closed surface is possible only when it encloses the charge. Now there is no charge inside, so flux should be zero. Or you can argue in this way. How many electric field lines enter the conductor? Same number of electric field lines go out of the conductor. So the flux should be zero. A ray of light incident obliquely travels from medium 1 to medium 2. And if n21 is greater than 1, then what is the conclusion? Angle of refraction is lesser than the angle of incidence. Refracted ray bends towards normal. Okay, we'll see that. So if the medium 1 is here, medium 2 is here, and if a ray of light is traveling from medium 1 to medium 2, we say that this is the angle of incidence. We don't know what is the angle of refraction. We write refractive index of medium 2 with respect to medium 1 as velocity, the ratio of velocity of light in the first medium to the velocity of light in the second medium. If V1 is the velocity of light in the first medium, V2 is the velocity of light in the second medium, then N21 is V1 by V2. They suggest that N21 is greater than 1. If N21 is greater than 1, then V1 should be greater than V2. What does it mean? If velocity in the first medium is greater than the velocity of light in the second medium, then this should be rarer medium and this should be denser medium. If V1 is greater, V2 is smaller, then V1 should be rarer, V2 should be denser. When the light travels from rarer to denser, you know, this formula continues like this, sin I by sin R, so on. If it is so, then the ray is moving from rarer to denser, it should bend towards the normal, angle of refraction should be smaller. So it's in a series you can answer. Angle of refraction is lesser than that of angle of incidence, correct? Refracted ray bends towards the normal, correct? Speed of light is lesser in medium 2 than in medium 1. So definitely correct, because V1 is greater, V2 is less. All the above are correct. This is the correct option. Similarly, going to the next question. Oh, here answer is given. I should have blocked it. Okay, forgotten. A ray of light incident obliquely travels from medium 1 to medium 2. And if N21 is lesser than 1, N21 is lesser than 1 means V1 by V2 should be lesser than 1. That should be V1 is lesser than V2. In the first medium, velocity less means it is moving from denser to rarer medium. So when a ray of light travels from denser to rarer medium, it bends away from the normal. Angle of refraction is greater, correct. And the refracted ray bends away from the normal, correct. Speed of light in the medium 1 is, one is more than, yes. Speed of light is lesser in medium 1. Yes, lesser in medium 1 because it is denser than the speed of light in medium 2, correct. All the above are correct. So just a small, the problem here is, you may understand, you may be knowing all these things, but in the examination hall, you must be there enough and you should be strong enough to answer all these things. Okay, sixth one. N21 is the refractive index of medium 2 with respect to medium 1. Then we can write the formula N21 is equal to V1 by V2. And if N12 is the refractive index of the first medium, yeah, N12 is V2 by V1, then how do you relate them? You know that this is N21 is the reciprocal of N12, but you have the answer. N12 is 1 by N21. Seventh one. Select the correct statement among the following. Okay. A ray parallel to the principal axis of the lens after refraction passes through the second principal focus. Definitely it is correct. Any ray parallel to the principal axis passes through the focus. Correct. Correct one. A ray of light passing through the optic center of the lens emerges out without any deviation. Yeah. If it is a thin lens, any ray of light passing through the optic center passes undeviated. A ray of light passing through the first principal focus of the lens or appearing to meet at the first principal focus emerges parallel to the principal axis. Yes. So if you have a convex lens like this, and if you have a ray of light passing through the principal focus, it should appear parallel. In the case of concave lens, I can draw it here. In the case of concave lens, suppose you have a ray of light, if the focus is here, and if you incident a ray of light towards the focus, it should become parallel like this. So a ray of light moving towards the focus on the other side should become parallel. So all these things, three are right. Yes. So which are options are here. So they are here. So you have to select which are true. Statement, correct statement. All the three are true. 1, 2, 3. Okay. Regarding sign convention, select the correct statement among the following. For erect image formed by a lens, magnification is positive. Yes. Sign convention, select the correct among the following. Yes. M is magnification is height of the image to the height of the object. That is the formula. And if the height is above the principal axis, then positive. Below the principal axis, negative. So for erect image, object, however, it is above the principal axis, image is also above the principal axis, it is positive. Correct. For inverted image, magnification is negative. Correct. If the magnitude of magnification is less than 1, image is diminished. Yes. If this is less than 1, what is the meaning? H dash is less than H. That image height is less than object height. Image height is less means it is diminished image. So all the three are correct. Correct statements are 1, 2, 3. Glass lens of focal length f and refractive index 1.47 is immersed or disappears. That lens appears as a lens in air, but as soon as it is put in a medium of refractive index same 1.47, the glass lens disappears. That is because the refractive index of the lens and the refractive index of the surrounding medium, they become the same. So it appears like a glass slab. The ray of light incident parallel moves parallel. There is no deviation at all. So a glass lens of focal length f, refractive index 1.47, disappears when immersed in a liquid of containing glycerin of refractive index 1.47. Focal length of the lens when immersed in the liquid is. Now you know the formula. 1 by f is equal to refractive index of the lens by refractive index of the surrounding medium minus 1 into 1 by R1 minus 1 by R2. Nothing happens to these two. But here is the magic. 1 by f is equal to, it becomes refractive index of the lens and surrounding medium are same. So what happens? It becomes 1 minus 1. So whatever this is, 1 minus 1 is 0. So 1 by f is 0 and f is infinity. Focal length becomes infinity. This answer. Because parallel rays emerge as parallel. They do not get focused at a point or they do not diverge at all. So they become parallel means they meet at infinity. Focal length is infinity. 1 by f is 0. Power becomes 0. That lens has no ability to converge or diverge the rays. Power becomes 0, but focal length becomes infinity. Option D. Select the wrong statement. A convex lens of shorter focal length has larger power. You know that power is equal to reciprocal of focal length. Convex lens of shorter focal length has larger power, correct? A concave lens of shorter focal length has larger power. That is also correct because power is reciprocal of focal length. A convex lens of larger focal length has smaller power. That is wrong. Larger focal length means, oh yeah, convex lens of, yeah, that is correct. Correct. The next one is also correct. A convex lens of larger focal length is also having smaller power. Correct. Power is independent of focal length. That is wrong. Power is dependent on the focal length. So option D. Select the correct statements. Power of a lens is positive for a converging lens. Yes. For a converging lens, F is positive, so power is positive. Correct. And power of a lens is negative for a diverging lens. F is negative, power is negative. Correct. Power of a lens of focal length 100 centimeter is 0.01 diopter. That is wrong because power is diopter when power is 1 by F. If F is in meters, power can be in diopter. Both are SI systems. So if you want to calculate the power of a lens of focal length 100 centimeter, you have to substitute 1 meter here. This is 1 meter. If you want to put the power in diopter, focal length should be in meters. 1 by 1, that is 1 diopter, not 0.01 diopter. That is wrong. For a lens, power varies with wavelength. Yes, definitely, because focal length depends on wavelength. For a lens, red rays are brought to focus far away, and blue rays are brought to focus very close. So focal length varies, power varies with the wavelength. So select the correct statement. Oh, it should be, here are the options. Correct statements are 1, 2, and 4. 1, 2, and 4. It is option B. 1, 2, and 4. Third one is wrong. 1, 2, and 4 are correct. Yes. If M1 and M2 are the magnifications of the image produced by two individual thin lenses in contact. There are two lenses in contact like this. Okay. If M1 and M2 are the magnifications of the image produced by the two individual thin lenses in contact, magnification of the combination. Okay. Magnification of the combination is the product of magnifications. M1 into M2. And of course, power is the addition of the power, P1 plus P2. And focal length is reciprocal of the equivalent focal length is 1 by F1 plus 1 by F2. So magnification is the product of magnifications, M1, M2. Magnification produced by a glass lens in air is found to be -1. The lens is. Okay, magnification produced by a glass lens in air is found to be -1. The lens is -1. If magnification is -1, then H dash is equal to -H. What do you mean by that? H dash equal to -H means object is above the principal axis and the image is below the principal axis, extended below the principal axis, and the sizes are same. So it is same sized inverted image, the meaning. Same sized inverted image. Negative sign says that it is inverted image. That can be produced by a convex lens. It's a glass lens in air, so it should be a convex lens. Convex lens can produce the same sized inverted image when the object is at 2F. When the object is at 2F, image is also at 2F. It is inverted and same size. So it is a convex lens. And you have got the answer for the next question also. Magnification produced by a glass lens in air is found to be -1. Object distance is 2F. Object should be at 2F. And there is no center for, there is nothing like 2F, F equal to R by 2 for a lens. So it is only 2F. Okay. 15th one. A plane wavefront is incident on a converging lens. The shape of emergent wavefront is. So regarding these wavefronts, you know that a point source emits spherical wavefront and a linear source emits cylindrical wavefront like this. And if you are at a very far away distance, both the cylinder and sphere will appear like a plane. If the source is at infinite distance, the wavefront received is a plane wavefront. So point source emits at a shorter distance, it emits spherical, linear source, so cylindrical, and at very large distances, it is a plane wavefront. But now the question is, a plane wavefront is incident on a converging lens. And you know, in a prism, if it is incident, a plane wavefront is incident like this, then that means parallel rays are put, which is equal to plane wavefront. They simply bend into different direction. They deviate, but this again, the emerging wavefront is plane only. So for a prism, incident wavefront is plane, emergent wavefront is also plane. What about lens? When a plane wavefront is incident on a convex lens, you know that the secondary wavelets which reach here, they have to travel less through the lens, whereas the secondary waves traveling here, they have to pass through more through the lens because thickness of the lens at the center is more. Here they have to travel less. So these wavefronts move forward, whereas these wavefronts move forward. These wavefronts move less. So these move little bit more. These move little bit more. So you will get a spherical wavefront after refraction. Since the wavelets, secondary wavelets passing through the center of the lens have to travel more, since the thickness of the lens is more at the center, they will lag behind. So they will form spherical wavefront. So as soon as they emerge out of the lens, you will get a spherical wavefront, and that sphere, if you take this wavefront as this is spherical wavefront, and if you draw normal to this wavefront, you will get rays of light. Those rays should reach focus. That means this wavefront should have a center at the focus. That means this wavefront should have a radius of curvature which is equal to the focal length of the lens. So remember, there are many points covered here. If parallel rays are incident on a convex lens, they converge and meet at focus. The point where they meet is focal length of the lens. And so if parallel rays, instead of parallel rays, according to Huygens principle, we will talk about the wavefront. If plane wavefront is incident on a lens, then after refraction through the lens, they become converging spherical wavefronts. That means this sphere goes on decreasing its radius and finally becomes zero. It converges at focus. Just after refraction, the spherical convergent wavefront will have a radius which is equal to f. Now, if it is a mirror, of course, we can answer some of the questions here. A plane wavefront is incident on a converging lens. Radius of the emerging spherical wavefront is. We have a question before that? Yes. This one, 15th one now. A plane wavefront is incident on a converging lens. The shape of the emergent wavefront is spherical. Converging spherical, yes. A plane wavefront is incident on a converging lens. Radius of the emerging spherical wavefront is f. It is f, focal length, because they should form a sphere, converging sphere, which will converge at focus. Okay. Then a plane wavefront is incident on a concave mirror. Okay. We will we'll take a concave mirror, which is bent like this. Incident a plane wavefront on this. So like this. Now, after reflection, these waves, secondary waves from the center, will reach the mirror little late, whereas these waves will reach the mirror little earlier, because mirror is bent with a concave surface like this. Now, so I'll use different color now. Yes, yeah. So after reflection from the mirror, the secondary waves which reach here, they move a larger distance here compared to the wavefronts reaching here, because they will touch the mirror late. The mirror is curved away like this. So these, when the secondary waves starting from here get reflected and reach here, secondary waves from here will reach a little bit back. So these waves are here, these are here, and these are here. So you will get a converging spherical wavefront. So when a plane wavefront is incident on a concave mirror, the reflected wavefront is spherical. So if I take this as a concave mirror, this as a concave mirror, and then the reflected spherical wavefront from the incident plane wavefront. So even the incident wavefront is plane. By the time the waves here reach here, it will be little late and they will be lagging behind. So the reflected wavefront will be like this. And if you draw the normal to these, they will be focusing at a point like this, yeah. So this will be the radius. Radius of the spherical wavefront, reflected spherical wavefront, will be the focal length, which is equal to, so they will meet at the focus. So radius of the spherical wavefront is radius of reflected spherical wavefront, converging spherical wavefront is, it is equal to focal length, which is equal to radius of curvature by 2 of the mirror. Radius of curvature of the mirror by 2. That is better. Radius of curvature of the mirror by 2. Radius of... So if you answer this question, a plane wavefront is incident on a concave mirror. Radius of the reflected spherical wavefront is, it is focal length of the mirror itself. but which is equal to radius of the mirror by 2. That is also okay. Okay. Self-induced EMF is also called back EMF because self-induced EMF is induced. That EMF is induced in order to oppose the cause. That's why it is called back EMF. Which component offers resistance to the flow of alternating current which is independent of frequency of AC? That resistance or reactance should be independent of frequency of AC. You know that XL depends on frequency 2 pi nu L. XC depends on frequency 1 by 2 pi nu C. Whereas R is independent of frequency. It has nothing to do with frequency of AC at all. Pure resistor. In the following graph, stopping potential is represented by the point. You know that this is the stopping potential V0, and this is the saturation current here. So this is represented by C like this. So better you study some diagrams and their parts, slope, something related to the diagram that may be asked. Okay. So thank you for watching. Thank you.